We are accustomed to expecting danger from outer space, a vast, nearly unknown realm hostile to humans. It's no wonder, given the colossal explosions, rapidly moving asteroids, comets, and black holes, all potentially capable of causing the Earth's destruction. But what about something tiny, like an ordinary sewing needle? What if it somehow found its way into space, accelerated to the speed of light, and collided with our planet? Hello, and welcome to Z. Please don't forget to subscribe and hit the bell icon. NASA scientists consider such a disaster unlikely because any object made of matter cannot move at the speed of light or faster. Nonetheless, let's delve into this hypothetical scenario. Today, you'll discover how dangerous small objects can become when properly accelerated and learn about another unusual end-of-the-world scenario. Our planet is constantly bombarded by various cosmic bodies, most of which burn up in the atmosphere unnoticed. Occasionally, celestial bodies enter the visibility zone and cause a stir, like the Chelyabinsk meteor or the asteroid that caused the extinction of the dinosaurs. However, these celestial bodies move relatively slowly on a cosmic scale. For instance, the Chelyabinsk meteor traveled at a speed of 60,000 to 69,000 kilometers per hour, 37,000 to 43,000 miles per hour. Now, imagine scientists report alarming news. An unknown object is approaching Earth at the speed of light. It's very small, the size of a needle or a grain of sand. If you think there's nothing to worry about, think again. What seems absurd at first glance poses a severe danger to our planet. The consequences would be catastrophic due to the object's immense speed. Consider a car traveling at 50 kilometers per hour, 31 miles per hour, hitting a person. The person might survive. Increase the speed to 65 kilometers per hour, 40 miles per hour, and the collision could result in death or severe injury. The speed of light is nearly 300,000 kilometers per second, 186,000 miles per second. Visible light, electromagnetic radiation, and possibly gravitational waves travel at this speed. Scientists believe massive particles can't move at the speed of light, only close to it. For instance, protons are accelerated to near light speed in the Large Hadron Collider. A needle or a grain of sand moving at the speed of light would be deadly. It wouldn't burn up in the atmosphere or explode mid-flight. The object's structural integrity would disintegrate, becoming a cluster of atoms passing through the air. The real danger lies in its kinetic energy. A grain of sand accelerated to near light speed would have the kinetic energy of an object weighing 100 tons falling from a 15-story building, akin to the Statue of Liberty's largest part falling from its pedestal. If such a needle hits Earth, would scientists have time to notice? It's uncertain, but the collision's kinetic energy would convert into explosive energy comparable to a 43-kiloton nuclear bomb. For perspective, the Fat Man bomb dropped on Nagasaki had a capacity of about 21 kilotons. The explosion from a needle would cause widespread destruction, similar to dropping an atomic bomb on Manhattan. The needle bomb could penetrate the ground, creating a massive crater. A plasma cloud would spread from the entry point, releasing energy and particles from the Earth's crust, forming a colossal fountain of matter. The resulting heat would devastate the surface, potentially tearing the Earth apart due to the immense energy exceeding the planet's gravitational binding. Alternatively, some physicists believe the needle's kinetic energy and inertia would allow it to pierce through Earth without significant damage, causing minor earthquakes at most. Humanity would likely survive. What if the needle hit a person? The probability is small, but it would be akin to the Statue of Liberty falling on someone. The needle's kinetic energy would destroy cell bonds upon contact, creating a nearly perfect hole in the body without severely affecting vital organs. The wound would likely be cauterized by the heat. The concept of a needle hitting the Earth at the speed of light is a fascinating thought experiment that challenges our understanding of physics, energy, and the nature of the universe. While the premise itself defies the laws of relativity, since, according to Einstein's theory of relativity, no object with mass can travel at the speed of light. Exploring this hypothetical scenario allows us to delve into the extreme consequences and physical laws governing high-energy impacts, relativity, and the speed of light. Einstein's theory of relativity establishes that as an object with mass approaches the speed of light, its relativistic mass increases asymptotically. This means that it would require infinite energy to accelerate a needle, or any object with mass, to the speed of light. Hence, the scenario of a needle traveling at light speed is purely theoretical and serves as a thought experiment to explore the implications of such an event. Energy and impact. If we momentarily set aside the constraints of relativity and imagine a needle traveling at the speed of light, the energy associated with this needle would be astronomical. The kinetic energy of an object is given by the equation equals 1, 2 E K equals 2, 1 mv 2. However, at relativistic speeds, the energy calculation must account for relativistic effects, leading to the expression equals gamma 2 minus 2 E equals gamma mc 2 minus mc 2, where gamma is the Lorentz factor, m is the mass, and c is the speed of light. For a needle moving at light speed, this energy would be enormous, leading to catastrophic consequences upon impact. Consequences of impact. Upon hitting the Earth, the needle would release its immense energy in an extremely short duration, essentially behaving like a particle collision at a colossal scale. The impact would result in an explosion of unprecedented magnitude, far surpassing any nuclear bomb ever detonated. The energy release would vaporize the needle and create a blast radius of global proportions, likely causing massive environmental destruction. Blast wave. The impact would generate a blast wave that would propagate through the Earth's atmosphere, creating shock waves similar to those observed in meteor impacts, but on a far greater scale. The shock waves would cause widespread devastation, flattening structures, and leading to significant loss of life. Thermal radiation. The release of energy would emit intense thermal radiation, potentially igniting fires over vast areas and causing severe burns to living organisms within the impact zone. The thermal effects would be immediate and far-reaching, contributing to the overall catastrophic impact. Seismic activity. The energy from the impact would also be transmitted into the Earth's crust, causing massive seismic waves. These waves could trigger earthquakes and tsunamis, leading to further destruction and loss of life, particularly in coastal regions. Atmospheric effects. The explosion would likely eject a significant amount of debris into the atmosphere, creating a thick layer of dust and aerosols that could block sunlight. This could lead to a dramatic cooling of the Earth's surface, a phenomenon known as impact winter, which could have severe implications for global climate and ecosystems. Long-term consequences. The immediate devastation caused by the impact would be followed by long-term environmental and climatic effects. The alteration of the atmosphere and the potential for global cooling could disrupt agricultural production, leading to food shortages and potential famine. The destruction of infrastructure and ecosystems would take decades, if not centuries, to recover from, fundamentally altering the course of human civilization and the natural world. Theoretical and philosophical implications. While the scenario of a needle hitting the Earth at the speed of light remains a thought experiment, it highlights the immense energy contained within objects moving at relativistic speeds. It underscores the importance of understanding and respecting the laws of physics that govern our universe. Additionally, this scenario prompts philosophical considerations about the nature of energy, the limitations of human technology, and our place within the cosmos. In conclusion, while a needle cannot realistically travel at the speed of light, contemplating such an event allows us to appreciate the formidable power of relativistic energy and the potential consequences of high-energy impacts. It serves as a reminder of the profound and often destructive capabilities of energy when unleashed on a massive scale, urging us to further explore and comprehend the intricate laws that govern our universe. In summary, should we fear needles traveling at the speed of light? Everyone will decide for themselves. Nonetheless, let's hope extraterrestrial civilizations are advanced enough to avoid such scenarios. If you enjoyed this discussion, give it a thumbs up, subscribe to the channel, and click the bell to receive notifications of upcoming interesting videos. Thank you for watching and see you next time.